Yeah, good morning. Today we're going to talk about undirected graphs. And the introduction that I'm doing to graphs is basically paying lip service to it because you will learn a lot in the algorithms course. But nevertheless, let us look at what an undirected graph is. As is obvious, if I have a set of vertices A, B, C, and D, then a graph like this without an arrow is an undirected graph. Okay, this is an undirected graph. So just as before, let's have some definitions. Here again, we define the graph G as B, E, set of vertices and edges. Each edge in G is unordered. Tell you in a minute what it means. Is unordered. Remember in the directed graph when we said if there is an edge u comma v, that means there is a path from u to v and no more. Here, if u comma v is undirected, then so is v comma u, or u comma v equals v comma u. That's what we mean. That means it's like a bidirectional edges. V is adjacent to u and u is also adjacent to v. In communication networks, this would be called a full duplex connection. The edge v, the wedge u comma v, is said to be incident on both vertices u and v. Okay, that's the most important takeaway. A path, again, just as before, Bn has an edge from Vi to Vi plus 1. It's an undirected edge, okay? And which is incident on both Vi and Vi plus 1. That's the most important takeaway. Path length, if there are n vertices, is n minus 1. And a simple path, just as before, V1 to Vn, where the vertices are distinct, except possibly the first and the last. But there's a slightly different notion of what a simple cycle is. Sorry. Okay. And a simple path, except possibly as the first and last, which can lead to a simple cycle. Now, the important point is that a simple cycle will see, remember in the directed graph we said a simple cycle can be even one edge. Here a simple cycle should be at least of length 3. Right? We do not allow, edge, vertex to itself, self paths like this because we don't have directed. And V1, V2, and V2 back to V1. This will be 2. This is also not considered a simple cycle. So you need at least 3 vertices. V2, V3. So you're looking at least 3 edges in a simple cycle. Okay. And if I have, so I can have something like V2W, W to Z, and Z back to V is a cycle. Is a simple cycle. Okay. Now, a graph is considered to be cyclic if it consists of at least one cycle. Okay. So if I look at this particular graph here, surely it has 1 cycle, 2 cycles, and 3 cycles. Okay. And so in that example, what do we have? We have ABDA is a cycle. Come on down. Okay. A graph is said to be connected if a graph is said to be connected if every pair of, if for every pair of vertices we have a path. Okay. And then of course there's something called K connectivity, which I don't want to go into, but just give you an example. There are some other notions of connected graph too. Let me, something like this, for example. If I take out this vertex, for example, then this will cause the graph to be disconnected. And then this one with one vertex itself, it got disconnected. You can also remove 2 vertices, and this will also cause it to get disconnected. But we look at the minimum set that's required for disconnecting the graph. Then you call such a graph K-connected graph, which essentially says what is the minimum number of vertices that need to be removed to get the graph disconnected. And There are some other notions of a connected graph where some people even refer to this graph as a unconnected. They call this also an unconnected graph because if you, for example, you can have, for example, suppose I remove this edge, I can have two connected components. I'll tell you what we mean by a connected component in a minute. Okay. For this, we need a definition of what is called a subgraph. And let's see what a subgraph is. We need to define what's called a subgraph. And let G equal to V comma E be a graph. And a subgraph G prime equal to B prime comma E prime is a graph where B prime is a subset of E, and also E prime consists of edges U comma W in E such that U comma W are in B prime. Okay. So if E prime consists of all the edges V comma W in E such that both V comma W are in B prime, then G is prime is called an induced sub graph. Okay. Then for example, if I take this, go back to this graph again, then if I remove the vertex D, then this consists of all the edges between A and B, and this is what is called an induced subgraph. Okay. And a connected component of a graph is a maximally induced subgraph that is a connected and induced subgraph. Okay. In the example, A is the only connected component the graph. If I go back to this picture, what do I mean by here? Let me call this A over here. So you're talking about a maximally induced subgraph. Then one important point that I've missed over here, this subgraph which we are talking about cannot be a proper subgraph of any other connected component of G. Okay, so this is something that is a bit difficult to understand, but we will use whatever we require. So what we talked about here when I made two components over here, this is called, this removal of this edge is called a cut edge. You can also do a vertex. If I remove this vertex, for example, it will cause the graph to be disconnected. So you have, we call it disconnected because it's not giving you, and these three nodes will be connected. Okay, so this causes the graph to get disconnected. And this vertex here is called a cut vertex. It can have, of course, more than one cut vertex. For example, even this can be a cut vertex for this original graph that we started out with, had these edges. Okay, this is just for definition. And I must tell you, these are actually cut vertices and cut edges are actually extensively used in circuit theory. Used in circuit theory, again beyond the scope of this course. Okay. Now, the next thing that we want to talk about is we can create what is called, if you have a connected and acyclic graph, then such a graph is called a free tree. Okay. So for example, this graph is a free tree, no cycles. Then a property of free tree, we need this because I'm going to do the minimum spanning tree algorithm. A property of free trees is that every free tree with n greater than or equal to 1 vertices contains exactly n minus 1 edges. Example, here 6 vertices, 1, 2, 3, 4, 5. Okay. If we add an edge to the free tree, it will form a cycle. Will form a cycle. Okay. Can prove this property either by argument or by induction. I'll just give this particular argument for you. A free tree with one vertex has 0 edges because it cannot connect to anything else. Okay, this implies n should be greater than 1. A free tree must have edges, uh, must have vertices with edges incident on it. Okay, because it's a free tree. Otherwise, it will be disconnected. Okay. Suppose every vertex has 2 edges incident on it. Now, that means what? We can find a path where, let's say I'm going from B1, B2, BI, dot, PG, and so on. So now what I can do is, I can enter VI through one edge and exit VI through the other edge. Okay. Then what will happen? At some point, you'll have a Vj equal to Vi. Right? All right. This implies it is not a tree anymore, since it has a cycle. Okay. Representation of undirected graphs. Use adjacency matrix and adjacency list. Both representations are used. The difference will be because it's undirected. Take this particular graph that we were looking at. Something like this. The given graph have a symmetric matrix. This is the path from A to B. There's also a path from B to. In the graph that we looked at a little earlier, this is what it will look like. Adjacency matrix representation. What do we have? We have A, B, C, D, and I have, let me say this, A, B, C, D, A, B, C, D here, have B to D, and I have from B to A to C to D, and I have C to B and C to D, I have D to A, B, and C. Okay, so these are two representations that we have. And as I said, our objective is to compute what is called the minimum cost spanning tree, and we'll talk about that.